Thanks for showing up. Yeah, it's nice to be here. Let's get into it. So what's in the cloud? We'll be talking about Azure Cloud here. So let's look at the agenda for the today. So quick introduction about me, what I do, my background, introduction about what we are going to be talking about.
Good morning, guys. Welcome.
Okay. Yeah, then a quick introduction about what we are going to be talking about today, why traditional threat hunting doesn't really work in today's cloud world. Then looking a deeper dive into O365 logs, what are the schema looking like, what are some of the fields that we should be looking for, things that we should be taking care while doing threat hunting. Then I'll actually show you my Jupyter notebook where we'll deep dive into doing some actual threat hunting, using some machine learning here and there, and trying to figure out anomalies, and then followed by some takeaways and references. So my name is Iyer. I work as a security engineer at Amazon. I do a lot of coding, build pipelines, do a research, and whenever I think my research is really good, I write a technical blog about it. I maintain a couple of open source repositories for various organizations, support open source, and a huge advocate for data privacy. Outside work, I do a lot of marathons, triathlons, watch a lot of anime, read a lot of manga. You should be able to find me at Iyer on Twitter, Medium, LinkedIn, I think pretty much everywhere. Disclaimer. The views, opinions, and content presented in this presentation are solely my own and did not reflect the views, policies, or positions of my employer or any affiliated organizations. The presentation is based on my personal research, experiences, and perspectives and should not be interpreted as an official statement from my employer. Had to put that out there. Now, let's get into the introduction part. So threat hunting, let's read about the definition, what it says. Basically, umbrella term for the techniques and tools organizations use to identify cyber threat hunting. So basically what we do is try to be proactive. We don't want to be reactive, which is basically something happened and then react to that. But we want to be like proactive and detect those threats, early stages of the kill chain, or if you talk in terms of MITRE ATT&CK framework, we want to detect them in the initial access or the execution phase, not in the C2 or the impact phase. So how early can we detect those threats and react to them? That's the whole idea about threat hunting. The traditional threat hunting was more focused on the expertise of the analyst or the threat hunter who was performing that investigation. But the modern threat hunting is more focused on automated tools, enriching those things using CTI, a lot of automation, which actually helps get the job done in a way better way than traditional threat hunting. Types of threat hunting or the classifications, we classified them into 3 different types: structured threat hunting, unstructured threat hunting, and ad hoc. Structured is when we are looking for TTPs. When I say TTPs, those are MITRE attacks, tactics, techniques, and procedures. Unstructured is when we are looking for IOCs, which is basically a breach occurred somewhere, and then your customer runs to you and be like, oh, these are some IOCs provided by some research company or CISA advisory or some other platform. Can you just run it against my infrastructure and see if any of these IOCs are getting back a hit or not? Ad hoc is basically when your customers say, oh, my third-party vendor got hit by a ransomware. Can you just make sure that I am safe? So you do ad hoc on demand. Structured is looking for TTPs, and unstructured is looking for IOCs. Limitations of threat hunting. Why traditional threat hunting does not work in today's world? The first thing is too much data. Earlier, we used to look at 1 terabyte of data per day. That's the maximum an organization is generating. But today, 1 terabyte is like generated in an hour. So how are you actually going to look for threats in the abundance of data? Way too much data being ingested into your cloud. The schema is not defined, and then it's going into some data lake or object storage. How are you actually looking for threats in that vast amount of data? You cannot expect a human being to actually sit through and go through all that data and figure out those threat hunts. That's why automation is needed to help you aid that threat hunting investigation part. Limited scalability. Again, a lot of data, so your threat hunts or the detection engineering queries, if you are using Splunk or KQL, any of those platforms, when you write those queries, it's very important to make sure that your queries are fine-tuned to look for specific things, which means if you're using wildcards and this like searching for everything and anything, that's not actually going to help you scale that to a larger level. If you want to look for something for 1 day worth of data, wildcards are good because it can fetch you results. But when you look for like 90 days of data, 100 days of data, more than that, a lot of data, wildcards are not going to help. static nature of threat hunts, which is basically like every day the threats are evolving, it's dynamic, and then every day someone is coming up with a new vulnerability or a new pathway to actually do the exact same thing. So if you are using signature-based thing, which is looking for a particular IOC hash, IP address, or anything like that, which is like very static in nature, it's not going to help you figure out what to look for. That's why we have to be like very dynamic. Inability to address unknown threats. Suppose you know there is a threat out there and this has this TTP, which is basically it's using this particular vulnerability. This is the pathway of getting into it. You know how to look for it because you know what it looks like. But what if you don't know what it looks like a 0 day? You don't know how to look for a 0 day because you haven't seen that. How are you going to look for anomalies which you don't know how it looks like? So that's what we are going to be discussing here, how to look for some things which you don't know how it looks like. So the traditional or the modern thing in which the data flow, you have your log sources, it could be your endpoints, network, or cloud, O365, object storage, whatever that is. Your log source will forward all that data using forwarders into your data lake. In terms of Azure, we call it Azure Data Lake, or you can put that into a blob storage, wherever that is. Let's call it data lake or the database where all that data from your customers are coming in. And that is being fed into your SIM solution. But why am I not tapping my Jupyter notebook from SIM solution is because the data that goes into SIM solution is always filtered. You only need some data for which you have got detections or which you have got use cases. But so basically you have like 100 terabytes of data, you filter that down to probably like 70 terabytes of data, and then you put that into a SIM solution because the SIM ingestion costs you. So you want to reduce that. That's why we are not tapping at SIM, we are directly tapping at Azure Data Lake. And from your SIM, analysts will do your investigations, and that's a traditional flow of things. What we want to do is basically use Jupyter Notebook, tap into Data Lake, and do threat hunting. Let's look at a couple of things about O365 before we actually dive in and do that threat hunting, because we need to understand how it looks like before we start looking for what is bad. So in order to figure out what is bad, we need to understand what is a good thing or what is a normal activity. So O365 management API activity schema comes in two layers. The first one is a common schema, and the other one is service-specific schema. Common schema is basically any of those fields which is common across multiple services. Service-specific schema is like very service-specific, OneDrive, SharePoint, any of those services. You're specifically looking for things in a particular service. You're looking for Outlook, you're looking for SharePoint, you're looking for Azure. So you're only looking for specific service. You take care of those service-specific schema. If you're looking across Azure, across O365, then you go for common schema. File and page activities. Some of the fields which are like very interesting, which looks very interesting to me when I do threat hunting, file access and file downloads, which is basically if somebody has like hacked your account and has got access to your account, what is the behavior of file downloads? Are they downloading bulk, like 100 files at the same time, and then accessing files? Are they accessing sensitive files? Are they accessing SharePoint to which they should not be accessing to? So that's like very good indicator of how normal behavior of a user versus an outsider who has got access into your account looks like. Then Microsoft Weaver inside activities, user logged in and user logged off. That's basically a sign-in events, but these are like going into O365. The usual sign-in events go into Entra ID. These are O365, so these are like logged differently. Directory administrative activities, set domain authentication, one of my favorite things. Whenever somebody is trying to do a golden SAML, this field is actually very important. So if you see set domain authentication set to true by an admin, because you need admin privileges to do that. If that is set to true and you see that event being logged, then that's actually a very high indicator of there is something going on. The person who is doing that should have a very valid reason to do that, or else just suspect that that's an indication of a golden SAML attack. Start there, start your investigation. Exchange mailbox activities, it's all about like accessing those email items, new inbox rules and set inbox rules, which is basically when you try to create a new inbox rule saying that any emails coming from this domain, just forward it here or move it to a different folder. And when you modify that, it goes under set inbox rules. And when you create a new one, it goes into new inbox rules. Identity, Entra ID, Entra sign-in, and Entra provisioning. Entra audit is basically any changes that is being applied to your tenant. Entra sign-in is all about Azure sign-in events when you sign in. And Entra provisioning is all about resource provisioning. I think that's enough introduction. Let's get into Jupyter and see the actual stuff. So, okay, for starters, what I do is basically do some imports, basic things. Here I'm using pandas because I just have a smaller data set. I just want to show you how it actually works. When you do it in scale, you might want to use something like Apache Spark. And then instead of CSVs, you probably might want to use a Parquet format, which is way better in storage thing. But here it's just for a demo, so it's just going to use pandas and CSVs. So load the data set, which is file downloads, and then try to look for bulk downloads. What it basically does is look for any users who's doing like more than 100 downloads. Why should a user be downloading more than 100 files? And also apply a time filter, which is saying that 24 hours. That threshold is basically upon your environment. If you see a user having legitimate reasons to download 100 files, and that's a normal occurrence, you might want to bump that threshold up to 200 or 300. But that's just a fine line which you have to figure out in your environment. Why is the user downloading that amount of files in a short amount of time? There is no business use case for that. If there is, good, else flag it. Then what I do is basically just giving it some numbers here. So read the file download CSV, and it has got 360,000, yeah, 360,000 lines, and these are the columns or basically the features that I have. So what I'm trying to do is take the relevant fields, which is user ID, the file name, IP address, the user agent, and the size of the file. So these are the fields or features that I think is relevant for my detection. This is called feature engineering, which is select the relevant fields from all available fields. Then do some encoding part. Encoding is basically whenever we do machine learning cannot be done on characters or alphanumeric things. Machine learning is always like ones and zeros. So you convert your strings into numbers. Ones and zeros, basically matrix. Any machine learning is basically a matrix multiplication. So what you're trying to do is take your data sets, select the right fields, convert them into ones and zeros, or matrix basically. Then you do a matrix multiplication. So here what I'm using is something called one-hot encoding, and then the model that I'm using is a Gaussian mixture. Gaussian mixture is again unsupervised clustering thing. So clustering is basically you take all that data, plot that into a graph, and then it forms clusters. So anything normal or have similar behaviors get grouped into one cluster, and the ones which does not have like sit with those normal or centralized cluster go into the outskirts. So you know that, okay, those are some fails or events which does not sit with most part, and why are they not sitting with most part? We need to investigate those separately. So that's the idea here. Anomalies are basically using a score of 95, which is anything which sits with the 95% of the data goes into a centralized cluster, which does not sit with the 95% of the data, which means that 5% which is an off factor is an anomaly here. That's an assumption. You can always tweak that factor up and down. So here we see 507 out of 300,000 something. So if I have data set of 24 hours and I am flagging 507 rows, okay, good enough, but do I really want to throw 507 alerts to my tier 1 or tier 2 SOC investigations? That's actually a bit on the higher end. I don't really want to do 507 because 507 doesn't look like a reasonable number for one use case. 500 alerts a day for all the use cases might be okay, but for one use case, a bit too much. So that's why I don't want to do clustering. I don't want to do this one. Let's see if I have a better way of doing it. Oh, okay. Let's actually visualize and see what exactly was I talking about. The centralized cluster, the outskirts and everything. So here basically I take two fields because for any node you need like any line you need 2 points. Here I'm using user and user agent. So any user using a user agent, which is like looking like a normal user agent, like if I am using Microsoft Windows on a daily basis, and then one random day I decide to use MacBook. So that's a different user agent, and that should be flagged very clearly. So that's what is going on in here. So if you look at this graph, that centralized cluster is basically the 95% of the data, which has got some similar factors to each other, binding them together. And all the ones on the outskirts, they don't sit with the data on the center, which is basically, I'm using an Android device, which is different from my Windows device, or I'm using a Raspberry Pi or a Python crawler, any of those user agents which does not sit with the regular things that I'm used to in that data set is being flagged on the outskirts here. So it depends on what fields that you want to use. I use user and user agent. You could use IP address. You could use, if you're using like file thing, you can use the number of files or the size of files, anything. So depending on what features work for you in your environment, choose those, play around with that. This is just a plug and play. Take this code, choose those fields, plug and play. Those were good when we were doing like one-to-one mapping. We knew what we were looking for. We find a threshold and then we find, okay, file downloads, multiple file downloads. Okay, I'm going to look for bulk file downloads. But what if I don't know what I'm looking for? I want to figure out something unusual going on in my environment and I don't know what it looks like. That's the case which most of us are trying to solve here, and that's where machine learning comes in. And here, what I'm trying to do is basically take the exact same data set, which is file downloads. And from file downloads, I'm going to select my features again, feature engineering, user, file name, IP, platform, and file size. So taking all those features, what I'm going to do here is take out the duplicate parts because I don't really want to deal with the duplicate parts. And then I'm going to use something called an autoencoder model. So autoencoder model, one of my favorite things, again, unsupervised learning, easy to train, easy to get outputs. The best part about this one is less amount of data. You give it like 30 days of data, 60 days of data, 90 days of data, easily trainable, easily deployable. So how it works is basically take all the input data set and then, so this is the actual logic of autoencoders. Take all the data set and then compress that to a lower dimension. Suppose it has got 100 dimensions, it is compressing that to like 10 dimensions and then expand it back from 10. So for image compressions or like file compressions and all of it, autoencoders are a really good use case. What we do is compress the input and recreate that. So anything which is actually a normal baseline activity will go into that compression and come back again in that same baseline. And suppose I'm talking about numbers here, right? Okay, 2, 4, 6, and 8. I compress them and then recreate it back. It's actually an exponential thing. So 2 will actually go into like something like 1 and come back again 2. But if there is a 30 there, 2, 4, 6, 8, and there is a 30, that 30 goes into a compression, and when I do an exponential expansion, it actually will outburst the other numbers, and that sounds like an anomaly. So that's the actual mathematical logic of how autoencoders work. So here what I'm trying to do is take all that fields that were relevant, all those fields, selected those, use an autoencoder model, and there is basically some encoding part, which is like using a mean squared error, ReLU, and all of those things, a bit to machine learning terminology here. But again, I'm taking that data set, running it for 50 epochs, and training and testing. So what it does is basically, I have that data set, I split my data set into training and testing. I keep 80% for training, 20% for testing. So train my data set on that 80% and use that rest of 20% to test out if my data set is actually working or not. Validation, again, same thing for validations, batch size of 32, which means for every batch, I'm taking 32 events and then running it for 50 epochs or 50 iterations. So here you can see some loss, validation loss, and then finally the output is 1, 2, 3, 4, 5. So basically, out of 300,000, I have 5 events which are anomalous. So clustering was giving me 500. Anomaly detection autoencoders, 5. So throwing 5 at my analyst is way better than 500. So this makes a lot of sense to write detection engineering in a way which is not gonna like trouble my tier 1 and tier 2 a lot. So what is this showing? Like let's take one more example and try to figure out what exactly is going on. So this was file downloads. Now let's look at file access. Anybody who has compromised my account, has got access into my Azure account, O365 account, will try to like browse around and figure out what files do I have access to. Not like downloading files, because that might, a lot of users think that bulk downloads will set a flag or set a reminder or an alert. So they don't want to do downloads. They just want to access and see if that user has got access to confidential data, like architecture of that, or some business or financial data. So here we are talking about file access. Again, features, very important to select the right features. So user, client, user ID, IP address, the application display name, which means what is that application which is being used to access that files, and the authentication type. You can choose your own fields. These were working for me, so I chose those. Same again, autoencoder model, trained for 50 epochs. I've got 267, a bit more than what I expect. The reason for this one is we have got way too many applications doing way too many things. If you actually know what is a normal behavior in your environment, which is saying that Microsoft Office uses OAuth to do some activity, perfectly fine. So what you have to do is create a list of known activities saying that this application is known to use this particular authentication method to do this, this activity. You can put that as a baseline, or you can put that as a fine-tuned normal behavior, feed that into this model so that the model knows those activities are perfectly fine, so that need not to be flagged. 267, again, not a great number, but not too bad of a number as well. This one is basically like after machine learning. Those machine learning use cases can be extended to any file types, any activities like sign-in logs, file downloads, or probably email access, or new email rules. Any of those Microsoft specific actions, you can apply those. Then we'll talk about something which is basically, if you don't want to do machine learning, too much pain, we'll just focus on some regular use cases which can be just deployed right away. These queries are written in Python, so easily convertible to like KQL or Splunk query language or whatever that is. So here we are looking for file downloads. We are looking for multiple file downloads in less than some minutes. So 180 seconds, I think that's like 5 minutes, and 10 files download. So 10 files being downloaded in 5-minute interval. How many users have been flagged? A couple of users have been flagged. 26 users, okay. Now if I just plot this graph and try to figure out so how many users are actually downloading files from a managed device, is managed device. So the field here, this one is important, is managed device. Am I downloading those files from my device, which is like registered, and I know that device exists in the Azure AD? So basically, I'm using a laptop, which is my MacBook, and I'm downloading files from that perfectly fine. What if I'm actually performing some file downloads from Android? Why is the user downloading files from Android? Or why is the user downloading files from an operating system which is not registered before? That's basically a question that needs to be answered. That's why this graph is actually going to help. I'm a huge fan of graphs. Basically, if you look at terabytes of data in a tabular format, doesn't make much sense. But if you actually plot that into a graph, a simple graph, it does make a lot of sense. So here, what it does is basically you have got 2 different clusters, and these 2 different clusters are managed devices. Of like, is that a managed device? Yes. Not a managed device? No. And those things in between are basically some things that needs to be looked into. Why is there a third thing, which is like downloading files, which is not known? I don't know if it's like even okay in the environment. Is there a good business reason for that? Why is that happening? Things like that. These graphs, so good. This one, I didn't really want to like make it too complicated. That's why the label is off. If you actually look into the code part here, it basically says the label is off. If you turn on the label, set that value to true, you can exactly see what is that node representing. Inbox rule manipulation, this basically says anybody who's trying to do some manipulation in your O365 Outlook environment. So we are looking for add inbox rules, modify inbox rules, and new inbox rules, which is if I set a new inbox rule saying that any email from, suppose this person, CEO of this firm, forward that to a Gmail account. That's, if I add that rule, any email that comes in a business confidential information, or any email that has got some keywords, forward that to Gmail, basically exfiltration. So look for those things. Federation service, I talked earlier. Set domain authentication, very like high indicator of a golden SAML attack, so look for this one. Phishing and malware detections. So Microsoft has this capability where any email that comes in, Microsoft will flag it as a phishing email or a spam email. So the thing is, okay, it's actually phishing or it's spam, but we also have seen a lot of phishing emails which Microsoft does flag get into the inbox. It's not like purged or like taken out or moved into a spam folder or anything. It actually gets in. The idea behind this one is if you do this, it's basically taking care of all those things which are flagged as phishing, and now you have a data set which is known bad. Now that data set can be used to train your model saying that, oh, this is how a phishing email or a spam email looks like for your environment. Now that can be used to train your models to identify business emails versus phishing emails. What are we looking here exactly? If Microsoft.o365.audit.verdict equals to phish, and the event action is TI-URL click data, which means that phishing email has been clicked on. As simple as that. So we have got a couple of emails in here, and these are like known spam phishing emails and stuff like that, but good harvest of data. One of the questions that I usually get is when you want to train some really, really good machine learning model, you need bad data, how a threat looks like. Where do I get bad data from? Your own environment. You have a lot of malwares, phishing coming into your environment on a daily basis. Just extract that out, use that as a training data. These are basically just showing what exactly that is. So delivered a spam or spam. Azure AD risky sign-ons, one of my favorite things to do actually. So risky sign-on is anytime a user signs in into an Azure application or an O365 application that is being logged. So what Microsoft does is looks into the IP address where it's logged from, user agent where it's logged from, the location it's logged from, and also some other parameters that they use to classify a login as a risky login or a regular login. So what we do here is basically take that risky login. The risk state should be anything but none, which means at risk or like remediated risk or any of that. And then the app display name is a none value. So I've actually written this detection after working for an incident response for one of the clients where they actually got into the Intune account. They had admin privileges and ended up being a ransomware at the end. So this was basically app display name is a none value. They get in and then they actually logged into Office Home. So look for these parameters. This is actually one of the TDPs for one of the known APT groups. So this good. So now I know Azure AD and making sense. But what if my client uses an MFA, which is not Microsoft? If Microsoft MFA is used, then I know all those MFA activities will be logged into my Azure. But what if they are using Okta? If they're using something like Okta, then the MFA takes place outside of Azure and that will not be logged. So how are you going to correlate a login activity which started off in Azure, but the MFA happened in Okta? You need some fields which you can map to both those tenants. And that field is basically user principal name is what the username or the email ID is in Azure. And the exact same parameter in Okta is alternate ID. So what you do is basically look for all those data sets, both these data sets for the exact time frame. There might be some seconds delay because it starts here and then goes there. So time frame cannot be used to match it exactly. Take 1 hour of data. On the left-hand side, I've got Azure Logs. On the right-hand side, I've got Okta. On left-hand side, I use the user principal name. On the right-hand side, I use alternate ID to join those things and then figure out, okay, was the MFA successful? How was the MFA done? Was it an authentication, like authenticator application or a push notification or OTP code, however that is, and then you try and figure out a lot more things when you correlate two different sources, which is exactly doing the same activity. Yeah, I think that is the Jupyter part of it. Now let's move back. Some takeaways. Basically, whatever we looked into this slide, so challenges with traditional threat hunting, why traditional hunting does not work today and why we need to do something more than that. Jupyter-based threat hunting, I love Jupyter-based threat hunting because it's so easy to implement in any environment. You do not have to like buy a SIM solution or you don't have to set up your environment for that. All you need is basically download Jupyter Notebook or Jupyter Lab, set it up, read data from wherever that is available, database or S3 bucket or Azure Data Lake, anywhere. You read that data, you run your queries, you generate an output as a CSV. Now that CSV can be sent to your SIM solution, whether it's like Splunk or Sentinel or any other SIM solution, Elasticsearch. All you need to do is an API call, back to that sim solution. So you're running your detection outside your sim solution or enhancing your sim solution, sending alerts. If you don't want to use a sim solution, perfectly fine. Just send that to a monitor where your analysts are working on. Jira ticket or Hive, these are applications where you can send that alert to. Automating threat hunting methodology, the whole thing, it's a manual threat hunt that what we saw, but it can be like run on a cron basis. So every 24 hours, every 12 hours, just run these queries and then it'll generate an output, send it to Sentinel. Ease of adoption and integration, that is what I talked about. Open for questions. Yes, please.
Where do you get your use cases from? Do you just come up with them, or
These are some of the use cases that I wrote after I actually saw a lot of attack vectors. These are like specifically mapped to some TTPs of APT groups, their activities. So I look at those threat actors, see what they're trying to do, and then come up with the use cases based on what they're doing. Yes, please.
If you have like all of the data that you have in your data lake already in your SIM, or is there still advantages to pulling things out in the Jupyter notebook?
The advantage is all the data does not go into SIM. You always use a filter. But if you're sending all of that into a SIM solution, these things, if your SIM can support aggregated machine learning based queries, Splunk has a Splunk machine learning, you can run the exact same thing on Splunk as well. So these are basically methodologies which you can add to enhance the SIM capabilities. Run it on Jupyter, run it on SIM, run it wherever you want. Yes?
how long does it take you to train the models, and when you run them against real data?
Yep.
What is that time frame that you have?
Yep.
Because very often we're trying to hunt things fast. Time is a trade-off.
Yes. So these are trained on 7 days worth of data, and the training was done for 7 days, which is basically take the initial 7 days of data, do the initial training, and run that model for 7 days so it has a baseline. And again, that's actually going to start working, but if you need a really, really good output, less number of false positive, I'd say 30 days is a good bet. Yes?
So I did have a question, two questions actually. One, what is the recommended minimum resource to train this type of model with the data set you would know this use case?
Yeah, for Jupyter Notebook, which is able to query 1 terabyte of data, all you need is basically a 32 GB of RAM. You can run it locally, you can run it on your cloud. If you have GPUs, way faster.
Gotcha. So at least 32?
Yes.
So you can't skirt by with 24?
16 is good. It's just, yeah, 16 is good. It's going to take a lot of time. Sometimes the kernel might crash because you have way too many data. So what you want to do is like batch processing. Split that data into smaller chunks, do the training.
Okay, gotcha. And my other thing was, if you're already running something like Rita,
Yeah.
what kind of solution would you think of to marry these two together to bridge that gap? Like,
I think a lot of publicly available open source libraries do support like collaborating multiple platforms in Jupyter itself. So all you need is this Jupyter notebook. This can read from like multiple different sources. All you need is like specific wrappers around that function. Like any wrapper or supported SDK or like support developer tools. Like any tools, if it has a developer support or an SDK, pack that into Jupyter, bring that in, and then you can actually do a cross correlation or correlation in Jupyter itself.
okay, thank you.
References, thank you guys.